Hello there. My name is Xiaodong Lei. I'm going to present a tutorial on large-scale optimization and learning on behalf of Nabi, Yuan, and myself. And Nabi is a assistant professor from University of Leeds. Yuan is a lecturer from La Trobe University, Australia. I'm also from Australia, RMIT University. So this talk has two parts. The first part is on large-scale black box unconstrained continual optimization. The second part on combinatorial optimization. In this talk, we're going to focus more on the key idea of the work developed in this area and how they related to one another, rather than giving you the full detail. So for further information, we have provide references for you to refer to. Given the time constraint, I might have to skip some of the slides. We have a lot of stuff to cover. Okay, so here is a definition of optimization problem, typical ones. Minimization, you have objective function f, and vector x represent decision variables of n dimensions, subject to inequality and the equality constraint. But in this first part, we're going to focus more on the constraint, unconstrained optimization, because we're going to look at, in particular, the issue of variable interaction. In the second part, we'll look at more constrained type of, in particular, combinatorial optimization problem. So how large is large for large-scale optimization? This notion kind of has not fixed and changed over time. And we're living in a big data era, so now lots of problems considered a large scale are really tens of millions, or if not billions of variables. But what we generally say in the area of evolution computation is that if the dimension of which existing methods start to fail, then we consider perhaps is experiencing this bottleneck and cannot handle problem larger than that. Right? So if you look at in literature for binary variable, we have evolutionary algorithm that can handle up to 1 billion variables. Similar for integer variables, but for continuous real number optimization, we're talking about a few thousands, and anything go beyond that, and many of the existing metaheuristic algorithms start to fail. So that's probably considered large scale for evolutionary method. One of the particular challenge for large scale optimization is the exponential growth of the search space size, and we call curse-of-dimensionality. So two issues we need to look at. One is the search quality, and the other obviously is the efficiency. So in the literature, there are large number of work been attempt tackling this large scale global optimization problem. Roughly, we divide it into these following categories of different methods. And we have a survey paper that is provide a lot of detail on talking about all this method. So we're going to look at some of this method. One issue that have been studied continuously, even from the early days of genetic algorithm, is this variable interaction or linkage, or what we call them epistasis. The root goes back to even in biology, we talk about genetics. If we consider two genes interacting with each other, so they collectively represent some kind of feature in the phenotype space. So you have genotype and fitness represent the phenotype space. Both genes have impact contributing that genotype fitness So in another word, the extent to which the fitness of one gene can be suppressed, deactivated or activated by another gene. So they have some kind of interdependency on each other. So in the optimization area, if you look at here, the example, you have a function where the first one, f, you have two variables that they are separable. There are no variable interaction because you can pretty much optimize each variable independently without affecting the other. So this same landscape, if you rotate it, which is the figure on the right-hand side, nothing has changed, but only you rotate the fitness landscape, the function. So you get the second function, g. And what you see here is that the variables start to have this interaction, like an interdependency among each other. If you vary one variable and fixing the other, you're going to get somewhere that is suboptimal. If you want to get to this global optimal, global minimum, for example, you have to develop some strategy to co-adapt the step size in both dimensions in order to get there quickly. So this is what we call the variable have interaction with each other. You can notice this dashed line indicating this improvement interval. So when you rotate the function, that improvement interval start to shrink. Imagine you have many more dimensions. So this rotation will causing even more heart rate, right? So it will be even more challenging and difficult for algorithm to get to the global minimum. Two type problem we typically looking at. One is we call this black box optimization. That is assumption that you do not know anything about the problem. The only thing you have access to is the input variable and what's come out of the your objective function f, right? So you have a fitness value. In contrast, and here's we're referring to gray or white box optimization. So you do have some knowledge about the problem. You know how the constraint apply. You know some of the variable perhaps already there's certain interdependency you already known. So you can use that knowledge to do better, develop your algorithm and to solve them more effectively. For black box optimization, those knowledge is not accessible. The only thing you have is input and your output, and how we can figure out and learn about the problem structure. That's really the key question. So variable interaction is being considered as a very important aspect we need to take into account when we think about how we learn the problem structure. So this is related to even classic mathematical programming, like we talk about problem decomposition, dimensionality reduction, rotation invariance. If you have an algorithm that is rotation invariant, that means it can handle this sort of a landscape rotation. And even you rotate it, the performance of the algorithm is not going to deteriorate. So that's definitely a plus for any optimization method. Local search in mimetic algorithm, sometimes strong local search can help. And approximation and meta modeling allow you to approximate the problem better and using relatively cheaper cost. So linkage learning, we can consider there are roughly two, broadly speaking, two categories. Implicit method, that is the probabilistic modeling model, EDAs, Bayesian method, or even CMAES, which can learn the correlated step size of different variables. Or on the other hand, you have explicit method. You do look at a variable grouping. So if you have a way of learn how variables interact with each other, you can then subdivide them into different groups, and using that to help you to do better problem decomposition. That's why we call them a variable grouping method. Then you can plug in into some evolution method like this cooperative coevolution, making use of that decomposition information. Right. So in the explicit method like this EDA, generally speaking, they have this scalability issue. As you can see here, if you increase the number of dimension, the dimensionality of the problem, because EDA use sampling, you will start to getting erroneous, kind of inaccurate eigenvalue estimate. As you can see on the left side of the figure, on the right-hand side, where that's a true eigenvalue. So if you have this erroneous calculation of about eigenvalue, you can imagine when you do problem of dimensionality reduction, it's not going to be very effective, right? So people have attempted a different method like a random matrix projection, lower rank covariance, to allow you to reduce dimensionality and work in a lower dimensional space to be more effective. Okay, for in explicit method, then we talk about typical divide and conquer. So this sort of idea goes back to even philosopher like Rene Descartes. You know, if you have a large and more complex problem, think about how to break them down into smaller parts and tackle them individually. So really the divide and conquer idea. So that idea used across many disciplines. In computer science, we do sorting, or in classic optimization error, operation research, large scale linear program. We're going to look at in the second part some of this typical decomposition or relaxation method in mathematical programming. So for evolutionary algorithm, one idea, one paper that in particular stand out, and many people follow their work, is this paper published in 1994 by Porter and Dijon, corporate coevolution approach. Is really a framework rather than evolutionary algorithm. As you can see here, you have a large scale problem, high dimensional problem. Using this corporate coevolution framework, you can divide them into several different subcomponents. Each just take a small part of a chunk of the problem. Together, they form back to this large scale problem, right? So each subcomponent, then you can apply a typical genetic algorithm or any other kind of a metaheuristic algorithm to evolve to make them fitter over multiple iterations. So like here, you see this is one subcomponent. I can evaluate the individuals in a population by looking at how well they collaborate through this context vector, how well they collaborate with the best individual in the other subcomponent. So because you have a much lower dimension for one subcomponent, it's much easier to evolve than involving the entire problem together. So you can then involve this particular subcomponent, but you get feedback from how well it collaborates with other subcomponent. And you can do this iteratively over many cycle iteration. And also you can switch between them. So if you're evolving this subcomponent, you're fixing the other subcomponent. Whereas you then next time you're going to fix this one and evolve a different subcomponent. So you do this in a robin fashion. Over time, the overall fitness can be improved. So this is a corporate coevolution idea. And as I said, you can plug in any kind of a component optimizer, whether it's TSO or differential evolution, or even CMAES. And they can all make use of this collaborative framework to evolve the overall solutions. Of course, you have to look at it, how you coordinate this component optimizer in order to achieve that. So several questions we have to ask. One is how we decompose the problem even before we apply this cooperative coevolution. And once you know how to divide and conquer, have a subcomponent, how are we going to spend, how much resource are we going to spend on evolving each subcomponent? So computation resource, are we going to allocate equally, or are we going to be adaptive? And how you coordinate. So there are many different ways of doing this. And that also the question is, what decomposition is going to be best? So this is one of the key idea, as you can see in the subsequent slides, how we learn the variable interaction that will help us to do better decomposition, right? So this idea of variable interaction can be learned, right? And the key objective is to to minimize the interaction between the subcomponent, where we try to keep variables that interact with each other within subcomponent, right? At the same time, keeping the interaction between the subcomponent at the minimum. So there are, again, a large number of algorithms developed over the years. You can see there are more automatic methods doing learning automatically, or there are semi-automatic methods, or down to a very basic, like this random method, here purely dividing the algorithm in a certain subcomponent without any learning used. Here is its example. You can see here we have this graph showing the variable. You have 7 variables, and there are the arc indicating the variable they have interaction between each other. So x1, x2 interact with each other. Similarly, x1, x4, and x2, x4. And you have another group of variables interacting with each other, but between these two groups of variables, there's no link. So therefore, there's no interaction. So if you have an algorithm to learn variable interaction, you would like to identify and discover such variable interaction so that you can do a better decomposition. For example, consider them as 2 subcomponents. That will help you the next step to do optimization, right? The first step is learn the decomposition, how to do better decomposition. So if you do not consider any kind of learning of variable interaction, you can like what we're showing here, just obtaining a variable one at a time, but that's not going to be very effective because there are variable interactions between them, right? So here showing a better way, you can using finite difference method to discover this variable interaction. Therefore, I can consider them as 2 groups because I've learned. It's like you do optimization, but do it before first. First, you need to learn the problem structure or problem property, then make use of knowledge to do better on your optimization. So here we learn there are, in fact, 2 groups of interacting variable. Therefore, I can decompose the problem into two subcomponents. One is x1, x2, x4. The other subcomponent is x3, 5, 6, 7. Right. So then you can apply corporal evolution and evolve them continuously. Right. So one method used in the literature, as you can see, is this monotonicity check. Right. Basically, you look at one variable. This is showing the example of just 2 variables. For one variable, if I fix it, then for the second variable, I take 2 different values. That will give me this 2 point, right? At the same time, if I perturb on that first variable by a certain amount, then I can get the other 2 points. Now I have this 4 point that allow me to calculate the fitness based on that particular objective function, and that's what I get. So you get the fitness value, then you can do what we call this a monotonicity check. Between the fitness value, you notice there's some differences. From that, I can infer there's a potential problem, variable interaction between these 2 variables. So directly checking the fitness, right? So there are several different methods that pretty much are following this line of thinking. And the other method that's developed more recently is rather than looking at this fitness value directly, we calculate we call delta value. Here's what we call them differential grouping. So coming back to this, you would calculate the difference between these 2 points and the difference between the other 2 points, then compare this delta value, see whether they are equal or not. And we found that this differential grouping method to be more accurate than some of this monotonicity checking method. Okay, so this is really this equation here tells you these 2 delta values, whether they are equal or not. That allow you to make a further inference whether these 2 variables are interacting with each other. So here is a illustrative example. You can see for one variable, if I fix it 1 dimension, then I can calculate I perturb, then I can calculate the difference. Similarly, on the second dimension, I can have the same perturbed value, I can calculate the differences. Therefore, I get 2 delta value, and then I can compare the two, see whether they are equal or not. If they are not equal, I consider them to be non-separable or interacting with each other. Otherwise, they are separable. So then I'm using this, just here showing the kind of using logical reasoning, right? So if variables separate, two variables separate to each other, then I know the delta value can be equal. By this law of contraposition, you know P implies Q. Negation of Q would imply negation of P. So I would have this conclusion. I would know if two delta values are not equal, I can infer they are non-separable or interacting with each other. This epsilon value, just for the sake of a computing precision level, sometime you need to set a value. This is generally, this epsilon value is a very small value. Then if it's greater than that, you would consider them, they are different, right? So if it's less than this value, that means, you know, very plausible they are separable. So you can using deductive reasoning to make that sort of inferencing. So I will skip that. So differential grouping also have a family of algorithms developed along this line of things, like this linkar, like this subsequent work after differential grouping, this global differential grouping, improved differential grouping, extended differential grouping, this XDG, further provide more nuanced detection on variable that in particular they are, if they're overlapping or not. And most recently, this the recursive differential grouping. You also have several different versions that really improved the efficiency of the way you do grouping through this recursive decomposition. So several of these shortcomings for differential grouping method, that is, it cannot detect the overlapping function directly. So you have to do this pairwise comparison for all the variables that you have. So this can be computationally very expensive, and you're not differentiating whether they are overlapping or you lump them together if they have any kind of interaction. So there's a lot of checking. They can be very expensive. Also, they require this threshold parameter, epsilon. As I said, the computer have different level of precision level. Therefore, when you do a lot of arithmetic calculation, is whether there's an issue whether we need to whether we can find out it's a true zero, that truly these two delta values are equal or not equal, right? So this is epsilon values. If you set as a fixed threshold value, it can be problematic. Nice way, a better way to do is to do it adaptively. Then you can, depending on the problem, you can come up this kind of epsilon value adaptively according to that problem specifically, right? So that's with the better way. So we want to remove this parameter epsilon. So this is lead to us to develop this second version we call differential grouping, and try to look at improving the efficiency. So do not have to do all the pairwise comparison. As you can see this figure here, instantly we can notice for some this point, as we draw this 4-point perturbing one point on one particular variable dimension in order to establish this delta value. So when you do the delta value calculation, you notice that some of the variable, some of this point you do calculation, they are duplicate. You calculate them several different times. So if I can remember that, I don't have to do this sort of duplicate calculation. So like this point, A, B, and C, they actually get used 3 times. So we don't really have to. We can just calculate them once. And so if you imagine you have a very large number of variables and calculate pairwise, you know, whether they're interacting or not, you're going to save a lot of computation. So this is really what we try to illustrate here among the computation costs that you can save. So once you have this pairwise comparison, you know, calculating a more efficient way, like in this differential grouping tool, we also propose to use this we call interaction design matrix. So here's this matrix that you have you can tell whether the variable interact with each other or not. So these two values is the actual difference of that delta value, right? So it's really try to see whether that's greater than the epsilon, the threshold value you try to see. If it's greater than the threshold value, you have the next one we call interaction design matrix. Essentially, if it's greater than the delta, I set it to 1. What this really tells me is that I can now between pairwise, any two pair of variables, whether they interact or not, according to my epsilon value, right? The threshold value I set. But you can make as I said, the threshold value to be more adaptive to the particular problem. So efficiency, we have proven that it has to be at least even you consider this duplication of evaluation, at least you have to spend n times n plus 1 divided by 2 plus 1, that number of evaluation, in order to do between pairwise calculation. Anything that you do more than that for other considering, like improve the efficiency, accuracy for particular, right? But the minimum to do is this. This will be the lower bound. Yeah. Okay, so this further work on differential grouping, in particular this extended differential grouping, try to look at whether you have a second different type of a variable interaction that we call indirect interaction. So the graph showing here, this is a more direct interaction. You can do calculate the partial derivative to be able to figure out these two variables interacting with each other or not. So x1 interacting with x2, x2 directly interacting with x3, but x1 and x3, they're not directly interacting with each other. As when you do this sort of partial derivative calculation, you get a 0 value, but there's a chain effect between all of them. So therefore, if you keep in track that information, you can figure out that xi and xj are here, and x1 and x3, they are indirectly interacting with each other. So that information is especially useful when you deal with problem with certain small number of variables overlapping, like the Rosenberg function. Right? So here showing yes, this sort of extendable differential grouping still have some issues, like not be able to differentiate these two type of a variable interaction graph, right? So this will treat as the same. You still lump them together. So later on, then you can see the further work. We're looking at this recursive RDG, recursive differential grouping. That will be even better, make it more elaborate and be able to differentiate some of these differences. So this is a recursive differential grouping. That really it's a really a smart idea that is that you're looking at the problem and divide it first, not like an individual variable pairwise. You look at two subset of the problem, right? So then from within the subset, you pick two vector like here, the U and U1 and U2, and doing this kind of a delta value calculation to see whether they are interaction or not. And from there, then you can infer at least these two subcomponents which contain multiple variables, they are interacting with each other. Then you can do a recursively decomposition, recursively divide the problem further into subset and detecting whether the subset continue to have interaction with the current one. So this will help us improve the complexity compared with some other the previous differential grouping method. So this is definitely a very promising method, and shows it even have a better complexity compared with DG2. So DG2 also consider this, as I mentioned earlier, the computing platform that we have tend to have precision. Different computer system have a precision, and when you do a lot of this floating number calculation, you might run out with a number that is because they're small precision at a certain level. The computer wouldn't be able to differentiate the different floating number, right? So because of representation issue. So if you have a large number, that error can blow out of proportion. So how we detect that? And this will allow us to have a better way of guessing that, setting that epsilon value. So if I know, we have a way of figuring out this lower bound and upper bound of this E value, then I can know anything that is greater than this will be a genuine non-zero value. Therefore, I can set my epsilon value, that threshold value, adaptively. Is anything that is below this lower bound, then I can consider it a genuine zero value. Or anything in between, that will be hard to gauge. So now we're moving on. This recursive differential grouping method, they have several different versions developed, like RDG2, RDG3. RDG3, it has a more nuanced detection on particularly the overlapping function. So when you have an overlapping function, as you can see here, this x4 is actually a shared variable between two group of variables. In the method before RTG3, you tend to lump them together, still consider them as one, as no differentiation. So that will be one. So I wouldn't be able to do any meaningful decomposition here. The RTG3, we tried to break off the linkage here, like allocate this variable x4 either into one subgroup or the other, but you always have this linkage that broken off, so that you can divide and conquer, right? Do a decomposition, then apply your typical cooperative evolution method involving subcomponent. Then we show that in fact improve the performance in particular those overlapping functions like the Rosenberg function, and our result overall in fact shows better, not only the better accuracy efficient wise as well. So in the competition that held in CEC 2019, this Max method in fact is a winner. They rank #1 out of all the interests that we have in terms of grouping accuracy and the final performance of the method. So you can see in the literature different algorithm favored by different people, but differential grouping is the one that have been used a lot. And next is a random grouping, which does not use any learning. It's just simply randomly shuffling variable into some subcomponent and optimize from there. Still popular because it's, I guess it's simple, yeah. So this kind of a differential grouping method or family of this type of algorithm can be used for analyzing problem property, like this structure engineering problem. If you do this sort of interaction matrix, this is what you see the interaction matrix derived. Then you can analyze, you can learn better about the problem property, therefore help you to do better optimization in the next step. So here I might notice there is this diagonally, I can group the variable into maybe certain certain ways before I apply, whether it's a heuristic method or exact method. Yeah. So you can further extend some of this idea of variable even into the realm of for constraint handling and multi-objective optimization. Like here in constraint handling, this particular paper, they talk about we can have several this interaction metric. Again, they kind of learn to use this interaction metric, but even apply for the constraint that you have in this case, right? So this theta 0 is derived from your objective function reflecting the interacting variable there. And zeta 1 is the first constraint, and zeta 2 is the second constraint. And this one just combine all of them together. That allows you to derive a picture, this graph showing the interaction among all the different variables in the objective function or in the constraint, and that is available. For large-scale optimization, there's also benchmark developed and doing this sort of analysis of the linkage between variables. As you can see the reference listed here. Here is one particular example of using the famous DTLZ multi-objective test functions. So for F1 and F2, for DTLZ1 up to DTLZ4, you can identify there are certain variables. Depending on the objective you use, they have interaction among each other. So this arc really tells us variable 1 and the variable 6, for example, they're interacting with each other directly, right? So for the other multi-objective function, you have 4 objectives, obviously. Here, DTLZ5, DTLZ6, you can also notice there are interaction among different variables, or certain variables that are, in fact, they are independent, right? So that information can be very useful for, you can leverage that for your next step doing whatever optimization. And this is a paper by Xiaoliang Ma. And it's interesting, he looked at the variables in the multi-objective domain, right? They classify them into 2 types of variable, of diversity variable or distance variable. Then they look at the interaction among, in particular, the distance variable. So those variables will have an impact on how the solution converges toward the Pareto from. So you can do a decomposition purely just based on the distance variable, and this is the interaction graph you can see. So I basically have 3 different sub-components that I identify based on what you learn, interaction among the distance variable, right? Whereas the diversity variable, I've just put them aside as separate ones. So that's really interesting. And the weighted optimization framework continue to fine-tune, improve your performance of your method by applying some kind of weighting scheme. This is again in the multi-objective area. So for LSTO, we consider there's still a lot of potential research, in particular, the synergy between optimization and learning. As we can see in the second part of the talk, we're going to emphasize a lot more using machine learning, right? But also the synergy between mathematic programming and metaheuristic can be further exploited, right? So hybrid method, hybridizing metaheuristic with mathematical programming is also a popular research direction, and making use problem decomposition, and the way you design and customize your variation operator. You can, if you can, you should explore the problem structure and how you get that information. That is generally you can do that through learning, right? Interesting thing, there's still more research need to be done, especially in dealing with overlapping components when you have a large scale problem. Not to mention there are other issues, noise, dynamism, uncertainty, and constraint handling, obviously. So if you're interested in learn more details about some of these works, there's these 2 review papers that published in 2021 that have a lot of the details. So now I'm going to talk about the second part, with a focus more on combinatorial optimization, and especially using machine learning. So this is a typical, we know in real world situation there's a lot of combinatorial problem, and that we can consider routing, scheduling, knapsack, and very typical. They are widely studied, in particularly in operation research, right? So typically you have a problem like this, right? This integer linear programming formulation. You try to do this is a maximization problem, but you have constraint here, ax need to be less than b, but the x is considered to be an integer, right? So that's why it's hard. It's actually pretty hard. They tend to be NP-hard problem. The objective function and the constraint can be linear in linear form, but the x here is an integer. So this is why we call them integer linear programming. The challenge is, again, in recent years, we noticed that the size of the problem that we try to tackle for combinatorial is also increasing rapidly in the big data era, right? So it's not uncommon. You heard people talking about problem of, tens of millions or even billions of variables. So this MIP lab, we also noticed people have benchmarked and evaluating their algorithm, exact method, MIP solvers, and so on. And you notice even those benchmark use have increased dramatically. The size have increased more than 70 times since 2003 until 2017. Right? So how we tackle those problems is the urgent need. One approach that is considered by quite a few authors is to try to reduce the size of the large-scale problem, combinatorial problem. Then once the problem size is reduced, then you can solve that reduced problem much easier by a typical solver. Of course, if solving that reduced one also means that you have a way of you can come back to the original problem and solve that original problem, right? So how we reduce that problem, right? So here is, you can see the graph here on the left-hand side. Let's say it's a traveling salesman or orienteering problem. You want to identify shortest path. So large number of city of vertices, and to find this shortest path will be extremely hard. But if I can do a problem reduction and reduce to a graph like the one on the right-hand side, and the problem much more manageable, much more easier, and you can plug in a solver. So this just show the basic principle idea we try to follow. Do the problem reduction, but we want to do it in a way that we know we're solving the smaller problem, essentially equivalent to solving the original larger problem, right? So there are different approaches that are taken for doing this problem reduction. Exact method, try to look at just using mathematical analysis to derive a way of removing or fixing decision variable, and therefore to achieve this problem reduction, right? But sometimes they can be expensive, costly. And heuristic method is another one, of course, based on simple rules, a rule you derive from your knowledge in domain specific problem domain, or the machine learning method that you can learn from data that you gathered from previous experience in solving that particular problem. So yeah, one type of this is looking at the problem specific bound. Here we look at a weighted a maximum weighted click problem. You have this graph here. You can see that each is vertex have weight. So the optimization objective is to locate the maximum weighted click is these shaded, these three vertex, because they have a large amount of weight that you can accumulate, right? So this 5 plus 4 plus 3, that tells you this click that have to be, you have this vertex being neighbor with each other, adjacent to each other. So this is really defining that such a problem. You want to find the maximum click, and if you know the upper bound information about this each of these vertex you're looking at, the upper bound calculated with itself plus your neighboring vertex, then you can induce whether there are other vertex that have less value than that, then achieve your task of pruning those vertex away, and therefore you achieve the problem reduction. Or you can do linear relaxation in integer linear programming. If you tackle the integer programming directly, as you see here, it's NP hard. It's very, very challenging. But so people tend to do is to do a relaxation. You do a linear relaxation, linear programming relaxation. So you're changing this to a real number instead of an integer number here, as you see, and you can prove that the LP relaxation solution is the upper bound of the integer solution. So this bound information can be used further helping to solve to find obtain the final solution to an integer problem. Because LP relaxation, LP normally considered to be you have a very efficient algorithm available. You can apply MIP solver like C plus Groovy. They are well established, and basically you can solve more efficiently. But integer programming problem is not, right? So the other thing you can do is a Lagrangian relaxation. Sometimes, again, when you tackle large scale integer linear programming problem, they are very challenging, very difficult. So what you do is bring in some of this constraint. Like here, you see it's a knapsack problem. I can bring in some of this constraint here into the objective function, treating them as some sort of penalty. If they violate this is a constraint, then there will be certain costs associated with it. So this is allow you to remove some of these more challenging and difficult constraints because you can incorporate them into the objective function, forming what we call this Lagrangian dual, right? And depending on the lambda parameter, you have different duals. So now the exercise become you try to minimize because it's a maximization problem. You try to minimize this Lagrangian dual, right? As to series of minimization, then you try to find the smallest upper bound. Now again, will give you useful information that allow you to further infer and how close you get to the optimal solution in the original problem. Then the reformulation is another decomposition method in classic operation research literature. And you can, for some very large linear programming method, the number of variables is so large, it's very difficult to tackle them all at one go. So the idea is if you use this formulation, then later on you can see we do this column generation method. You can only treat one subset, which is a small fraction of the overall variable, one at a time, and solving them through some iterative procedure. So here you can see this is an example of a vertex calling example. So vertex calling problem, basically you try to look at this graph and try to make sure each vertex have a color, but neighboring vertex will not share the same color, right? The overall objective to minimize number of color, but you have all the vertex are covered. So that's your objective function. So this is can be also there's several different ways of formulating the problem. One is using this maximum independent set idea. Essentially, what you try to do is in this formulation is to minimize number of maximum independent set in such a way that each vertex will be covered by one of the maximum independent. So all the vertex will be covered ultimately, but the overall number of maximum independent sets should be minimized. So this is why you have this formulation. But the number of maximum independent can be so large. So this set S is so large, it's difficult to tackle in one go. So that's where we can see this column generation idea coming. So you will take the initial subset of this very large independent set, this maximum independent set. And only, so this is forming what we call restricted master problem, because this is what we call column, variable or column that use it interchangeably here. So because the number of column of variable is smaller, you can solve them much easier with the standard solver like a Groovy, right? So now you can solve this, what we call restrict master problem. From there, you have the primal solution, but you can also derive the dual solution. From the dual solution, you can then form what we call pricing problem. The pricing problem that would allow you to identify further in the pool of column or the variables, which one you're going to pick. You're going to enter that into the restrict master problem in the next iteration. So that allow you to calculate negative reduced cost, and you're going to pick that variable if they are most negative and they are, most negative. So you have another optimization problem we call pricing problem that in association, it's in connection with this primer problem you have at that particular iteration, right? When you have a restrict master problem. So you do them through multiple iterations. Every time when you have a new variable into the restrict master problem, you have to resolve that restrict master problem again, having a new dual, then forming the pricing problem yet again. Then in order to identify the next column you to pick to enter into the restrict master problem. So you do them iteratively until you cannot find a column that is less than or negative. Therefore, you start problem. You see, you will find the optimal solution, right? So it's an iterative process, and you have these two problems that link together. The restrict master problem and pricing problem goes hand in hand. Every time you solve the restrict master problem, and that allows you to formulate the pricing problem. And from pricing problem, you can feed it back to your restrict master problem because you enter a new variable, a new column, and forming this yet again a new receipt master problem. You do them a multiple iteration until you stop, right? You terminate. And this column generation, they can be embedded in the classic branch and bound method, forming what we call branch and price method. So at the leaf nodes of the branch and bound, you will do a column generation in order to tackle this large scale linear programming problem. You solve them, but it's only a solution to relax LP relaxation. So then again, in the branch and bound, you're going to compare with the incumbent solution and try to tighten the bound. Ultimately, you can then figure out whether you found the integer solution that is optimal or not, right? That's a branch and price. So second category, heuristic method. Well, heuristic method like a meta-heuristic or some of this hybrid method I would call, right? So one is this is a large neighborhood search, really just looking at a different way of defining this neighborhood. So there can be a lot of different variation because how we define neighborhoods can be substantially different based on different method. Once you have the neighborhood concept, then you can say I'm going to fix some other variable and only focus on evolving or improving that neighborhood, some optimizing the neighborhood. And over time, you can change that neighborhood, right? Then allow you to improve. So in some way, it's similar in some way to that cooperative coevolution we talked about earlier on, although it's in different setting. The other very well-known method is this construct and merge and search and the depth method, CMSE. It's more like a hybrid method. It uses sampling, probabilistic model, starting from you have an empty set and you gradually adding problem within subcomponent to this set. So it's a constructive approach, constructing solution gradually over time. Then at some point, then you can have a feasible solution. But the way you construct, you're adding more subcomponent is according to a probabilistic model that you can learn over time. And the other interesting one is this paper published in GECCO, and in fact we have several different papers in that series, is this concept we call merge search. Again, we talk about large-scale combinatorial problem. In this case, it's open piece mining problem, resource scheduling problem. So in Australia, they have open piece mining in Western Australia. They generally a very, very large binary integer programming problem, right? So that's as you see here. So the variable are either 0 or 1 because they're binary. So we notice that if you apply this population concept in the meta areas, we have a population, then you can actually learn from the population of the individual for each of the variable over some iterations, right? Whether that variable is changing or not, right? So we notice larger number of variables, they're not changing. Either they stay as 0 or stay as 1, as you see here showing this graph. So then we learn, okay, maybe that variable is not going to change in the future. Therefore, we can fix them. But for certain variable, if you notice they are changing at certain iteration out of the population I have evolved so far. Therefore, they might be some sort of a flexible or free variable we consider. That's more represented by this white space here, right? So then this is what allow me to reduce the problem dimension. So those variables are never going to change in my runs, right? I'm going to fix them, either 0 or either 1. What's left is this middle area. The variable that I do have some change that I can observe. Therefore, I'm going to focus only searching on that number of variable. So this is how we achieve problem reduction. You can reduce the problem size up to by 99%. Sometimes only the final problem reduced from you consider is less than 1% of the original problem. So you can see the amount of reduction is substantial. Yeah. So of course there are differences between these several different heuristic methods. And then the other interesting approach is using data mining idea, again to learn interest idea patterns in your data. Right? You can identify some high quality set, and using that pattern to guide your search in terms of problem reduction first. Then you optimize, And towards the end, you're going to expand that reduced problem back to the original solution. Frequent pattern-based search, again, along the idea of using data mining. So in this particular case, using, I think, the well-established data mining algorithm like association rule mining. You know, you have frequent pattern, frequent set that are occurring, and you can identify that. And that information can be very useful to help you to construct new solution or achieving problem reduction. So what we really want to talk about next is the machine learning method, because you can learn from, in particular, you can learn from the data that accumulated from successful run in the past. From this data, I can form typically supervised learning or maybe sometimes reinforcement learning method, right? To learn from the data, to tell me some of the variable, either they are very useful, I mean, whether they belong to a particular optimal solution because the problem already solved, or is unlikely. So that data can help us to learn that relationship, right? A particular variable, a decision variable, they actually can be part of likelihood of being part of a optimal solution or not, right? So we're going to look at that more closely. This is very much the method we developed in 2021 in a PAMI paper, but then we can extend our idea, in fact, in several different scenario, a different way of tackling different decision point in the process of doing optimization in combinatorial optimization problem, right? So typically, this is a generic approach. So we're looking at firstly, you solve some easy problem to optimality of particularly, let's say, the traveling salesman, right? So once you solve those problems to optimality, then allow you to look at the data. Then I can label a certain variable, decision variable. In this case, perhaps it's this edge in a traveling salesman situation, right? Whether they belong to an optimal solution because the problem already solved. Therefore, you can label those decision variable whether they belong to that class of solved problem or not, right? The next is you can define a set of features to characterize this decision variable. For example, an edge or vertex of a traveling salesman. Then you can learn. You can train your machine learning model to learn to predict, given that the data that you have, right? You can form this training data set with this class label that you know. So it's a typical supervised learning binary classification problem we're talking about. So you can train the model to learn, you know, whether decision variable belong to a certain class, either in the optimal or not in the optimal solution. Once that model has trained or learned, then you can use that to test, to predict in a new traveling salesman problem instance, for example, and look at in that unseen instance, the variable, whether they are, you can make a prediction whether they belong to optimal solution or not, the likelihood, right? So this is really the general procedure. As you can see, this is more concrete example, this traveling salesman. So when you do the training on the top half of the graph, right, then you can label them. Then I can establish a boundary, right? Try to establish boundary. So this is just called the decision boundary. This is the machine learning algorithm you try to learn, try to be trained, you know, to achieve. You try the decision boundary is supposed to separate the optimal solution from the non-optimal solution. Belong to the edge, belong to the optimal solution or not, right? Of course, you might make error. That's fine. But the goal is to, once you establish decision boundary, then I can use this model, right? Then to predict on unseen a new problem instance, then make prediction on each of this the edge, right? Which is our training example. Here's a test example. Yeah. Then I try to predict that because I have a feature defined. I can fit into my machine learning model, make a prediction of it to see that edge is like what is likelihood is going to belong to a optimal solution. If it's less likely, they tend to fall on the other side of the decision boundary. So this is how you achieve problem reduction. So I know those, you know, point represent the edge that further away from this boundary is highly unlikely to be part of the optimal solution. Then I can remove them confidently, right? So this is what we end up for the unseen problem instance. I can have a reduced problem, right? You can with less edge. So this is just a general idea of using this training and the testing to achieve the purpose of problem reduction. But you can apply that, in fact, in many different type of, not just confined to the traveling salesman. And using here is a typically we're using information from the graph to define the features for your machine learning algorithm. So either vertex or edge information regard to vertex or edge, or IIP integer linear programming feature in the IIP formulation, cost efficient information in your constraint matrix, information you can get from LP relaxation, for example, the reduced cost. And lastly, the statistic feature, we found is very, very important and very, very effective. That is, you can do sampling from the graph that you got, right? You can do some random sampling of feasible solution, because the feasible solution contain useful information, and a certain part of that feasible solution may provide, may appear more often than some other component. Therefore, you can get, you can learn from that. Your machine learning algorithm can learn from that, allow it to, further in the future make a prediction on unseen instance. So machine learning method we have tried like this, including the deep learning method, graph neural net, and some of course classic machine learning method. And this is on the traveling salesman. What you see the graph here is that we're using in this case we have 7 different category of traveling salesmen, ranging from easy to medium hard to hard or random. So this different category, which is trying to demonstrate if I can use one category, the instance that the training instance that derived from one category to train my machine learning model to predict even on a different category, right? Not only its own category, but also on different category. You can see whether the model can generalize very well or not, right? So this is to show that for easy problem we train on the top row, it can generalize really well on the easy instance, sometimes on its own category. This is not surprising. On the other medium or hard category, they might have some problem. So the color really shows the optimality gap. So blue the better, because that's just very low value approaching 0. And so, but if you have a medium instance, medium level of difficulties type of traveling salesman instance used for training, and you can notice the improvement about its generalization capability even on different categories, whether easy or extremely hard. The optimality gap has dropped, quite a lot. So this paper is a paper that we're showing we can generalize the machine learning model that you train on one category of traveling salesman over some other category. Not only is different character, slightly different character of traveling salesman, but also different dimension size, right? Problems is small, but you can generalize what you learn on the easy instance to harder, more challenging, unseen traveling salesman instance. So there's some other work, and this work interests using this multi-stage pruning. So you're doing this learning and pruning not just in one go, but through multiple steps. Feasibility optimality gap, that can be, it's important to have some feasible solution in the initial solution that allow you to further derive perhaps the bound, right? Using that bounding from a continue to improve it, that allow you to get closer to the optimal solution in the original problem, right? So this is just tells you that to have some feasible solution in the initial solution pool is very important. So deep learning approach is graph convolutional neural net. So what you fit into here in your deep neural net is a graph. So in this particular paper, you form your MIP formulation, right? But turn them and transform into some sort of graph, because this is generally this sort of graph convolution and expected. You have to have a graph type of information fit into the as the input nodes, right? Once you you have that done, then your deep learning model can learn to make a prediction. The guided search, the output will be some kind of probabilistic model to tell you which path to follow, right? Which promising path to follow in a tree search, like a branch and bound, so that you can doing that help you to prune the trees, right? To achieve problem reduction. And this paper also looking at the predicting optimal solution for binary variables. This equation shows that what they try to look at is, again, in a mean formulation, the variable that is most likely, they call them a stable variable. So if a variable tend to always be 0 or 1, will be identified by this formulation, the way you calculate it. They consider it a stable variable, whereas variable that fall anything that are more in the middle ground, we consider them a free variable. So if you can identify the variable that are most times very stable, either 0 or 1, and you can fix them or reduce or eliminate them out, right? So that's how you achieve the problem reduction and focus more on those more unstable or free variable. We applied this solution prediction idea we developed for the max weighted click problem to metaheuristics like the ant colony, and we demonstrate we can use this to boost the ant colony, like use it as some sort of warm up, right? Procedure, right? So instead of let you a standard way of doing ant colony, you start from scratch. You try to learn those pheromone matrix and heuristic weight matrix. Here we can let the machine learning model to learn from already solved a simple, like say, orienteering problem. From the solved instance, and you can form this supervised learning binary classification problem, as I mentioned earlier on, to learn from the solved instance what the edge will be most likely to appear in the final optimal solution in the unseen instance. So we can demonstrate that if we use learning approach, all this learning approach is far better than the standard ACO approach, even in the very first iteration. So this is the normalized objective value, I believe. So the smaller here, the value on this here is considered to be better. The this yellow one is based on linear SVM, which have the best performance. But all these machine learning models are better, far better than ACO, standard ACO, because what we do is we learn from the data, solve the instance, and we can have a far better starting point than starting from scratch, like you typically do in ACO. So this warm start idea that we use to achieve that. Okay, so adaptive solution prediction is a very recent work that we have done for this solution prediction framework. We try to make it more adapt by adding in the testing stage, not so much on the training stage. So this is pretty much the same as you've seen earlier on. You train your model from solved instance, but when it's come to make a prediction on the unseen instance, you can do better by using what your machine learning model predict to guide the search a little bit and doing several iterations just right here in the testing stage. You're not going to change the train model, but you try to learn from the search method confirm better solution. Therefore, I can using this statistic feature because I'm going to do sampling, and you have now access to better quality solution. Your sampling in defining the statistic feature going to be more accurate. So if you keep on improving them several times, in fact, you can improve your prediction here using the already trained model. So you can consider this as a way of some kind of online learning as well. And that improved prediction can further help your search method to find high quality solutions. So this is actually reinforce each other. So if you do them several iterations, overall you can get better results. So this is what we call adaptive solution prediction. Okay. Problem reduction for density walk formulation. you can also apply this idea about machine learning solution prediction. So in this very recent paper, just published in the ICLR this year, we demonstrate that you can, for this vortex culling problem, you can learn from, again, solve instance of vortex culling problem. Some instance, and we use this formulation that are using maximum independent set. So if you know they are solved, the maximum independent set really just like a decision variable you say early on. So I can again label them and see them, and then I define feature on this maximum independent set. Then I can treat it as a binary supervised learning scenario, construct my training instance, then carry out a proper learning using whatever machine learning model like we've seen early. So once that you have a learn model, then you can make a prediction on this unseen vortex culling problem. Again, you have max independent set, then you can figure out, this is what is the likelihood of that appear in the final optimal solution. Then you can put them, almost use them as a warm-up, as a startup, as a seeding mechanism for the column generation. So rather than in the traditional operation research treating, starting from scratch, here you have a much better position to start with, because what you learn from the solved instance, right, using machine learning method. So it goes through a very similar procedure, defining feature. Especially this feature we found is very, very effective. That's also quite distinct from some of the other solution prediction method, because I believe we are the only one that using this sort of a random sampling to extract useful information from a pool of a quality solution, a feasible solution. Okay, so going through this column generation, once you have done the reformulation that allow you to do that, so you calculate the feature, you can evaluate the quality of the feature using the train ML model, the model already learned from the solved instance. Then you can replace low quality maximum independent set with the new ones. So you can using crossover of some kind of variation operator to achieve that, or even doing random sampling, just randomly pick someone from the pool. So this is a one way. So this is actually because you're starting from scratch, from initial side. I did assume no knowledge about the solved instance, and you can do that. Or you can treat as a warm start, as I mentioned earlier, so that you don't start from scratch, right? Okay. The other work we did is look at the pricing. So for the column generation, remember we have a restrict master problem. That's the primal, but also you have a pricing problem you need to solve at every iteration is column generation. So that pricing problem sometimes can be NP hard and very challenging. So if you can apply machine learning to learn to predict kind of a solution for that pricing problem, again, you can achieve similar sort of task like doing problem reduction. So this is what we try to look at different part of the column generation, but now it's the pricing solution. So that's happen at every iteration of column generation. So you do the usual training, but on the testing stage, this is your restrict master problem, and you have the dual. You predict the dual solution, right? And then you look at what likely to be appear for that pricing problem. Here, the differences is that we have multiple maximum independent set that we can use. Instead of the traditional approach, just the most negative reduced cost, the column with that, we're using multiple ones. We found them, there's going to be some speed up, efficiency gain that you can get when you have a pool of sample to use directly. So we again, this paper is try to demonstrate that effectiveness of applying this pricing, learning in pricing, but this is happening at in the context of branch and bound at the leaf nodes branch and bound. You run column generation, so essentially this is a branch and price. And there are several other different papers but happening a similar event like here, you try to predict the optimal objective value. It's not necessarily just a binary classification, but here you treat it as a regression, right? And you can learn the useful information about bound information for the optimal solution, and then use that to generate useful cards to prune the search space. This is some other variation along this direction. Again, use predict information to form new cut or new bound constraint to further reduce the problem space. And this paper, yet again, showing using a regression model instead of a classification model, working on continuous variable instead of a binary variable, that you can still apply this idea of a solution prediction. Neural large neighborhood search, again, for large neighborhood search, this method looking at doing some kind of repair for an incomplete solution, so that allow you to have a valid solution, and so that you can continue on in that process of doing a large neighborhood search. Okay, so quickly just the summary. So exact method generally can guarantee reduced problem content optimal solution, but in many cases they are very expensive to run, right? So if you think about practicality, this is why sometimes heuristic method could be better in exact method, or machine learning based method, because they are approximation method, right? So they're not the exact method. You can, but you can learn from the data. Given that we're living in a big data era, then a lot of data is abundant data that we can use of. But we never we haven't reached a level that fully utilize all this data that are available around us, right? But the downside is, I guess, it will be difficult to prove the optimality because they are heuristic method. So their work developed, this is one popular direction, that is hybrid method, combined mathematical programming, metaheuristics, and machine learning. You can see this kind of increasing trend of people tap into several different traditional separate area, now combining ideas together to make it more efficient for large scale combinatorial optimization. And so I think there's a lot of room for further research using machine learning to improve traditional method. Now, this is only really the beginning. So this is only, in fact, we've seen paper in NeurIPS, triple AI. Yeah, some of this top machine learning model. There's only in the last few years. There's relatively small number of paper published. So we consider this is a lot of potential here, using machine learning to further enhance how we do optimization. Again, one challenge is how we can derive this optimality guarantee for inexact method. And this is a question yet to be answered. But there are a lot of room for, again, further we will learn from other areas, statistical learning, operation research, and approximation theory. The one good thing about machine learning is really generic. It can be generally applicable. They're generally applicable. They can be applied and adapted to all sorts of problem solving. In combinatorial optimization, there are a lot of this decision point. Decision you have to make branch and bound, what variable to pick, what node to expand. So if you have a solved instance, the data are available, then you can learn from this data that you have accumulated using a machine learning method, and use it to predict what's happening in a future scenario when you have a similar problem instance, right? So this is where we tap into using what's already been solved for future problem solving of similar type of problem. Of course, to have something like dealing with generically this integer linear programming still remain a challenge. Sometimes you have to do retraining. That can be very costly. But there's a lot of room for further improvement. we even can envision this future potential that maybe some of this machine learning technique can be incorporated into commercial software like a Groovy or Cplex. Okay, I think that's the end of the presentation. So Nabi and Yuan and myself, we will be more than happy to answer your question. If you have any, feel free to contact us, email. Yep, thank you.